Hello and welcome to the second webinar in the data science webinar series. Today's topic is how to select a model for predictive analytics with Dr. J. Kyle Roberts. A few notes before we get started. This webinar is being recorded and the recording will be emailed to you in the next few days. We will also be opening up this webinar for questions at the end, but feel free to go ahead and submit any questions that you come up with in the Q&A panel found at the bottom of your Zoom as we go along. A few introductions. My name is Rachel Mason. I am the marketing specialist here at Teknion Data Solutions, and Teknion is happy to be hosting this webinar as a part of our larger webinar series covering topics such as data pipeline, data science, visual analytics, and then strategy. So be sure to check those out and register for any upcoming webinars. And at this time, I'm going to hand it over to Teknion's data scientist, Dr. J. Kyle Roberts.
All right. Well, thanks, Rachel. I appreciate getting to be able to share with y'all. Again, as you know, we've probably maybe seen you before on a few of the other webinars that we've done. And this one's actually really timely for us because we continually get asked this question of, hey, how do I know which model to pick? And how do I know if a model is good and is it working well? And lots of questions like this. So the first of those questions is what we want to address today, is that how do we select a model? And then later on, we're going to get into how do you know the model is still working? You know, how do you monitor the model? Things like that. So really just today, this is kind of a high level. We'll start to get into the weeds a little bit at the end. But just wanted to show you, look, how do you grab a model specifically when you're wanting to do predictive analytics? So having said that, we won't be doing things like k-means or let's say principal components, because we're not really pushing those out into production. That's kind of a data wrangling, if you will, and so when we're trying to kind of do data reduction, we might use some things like that. But a little bit about myself, and so I've been at Teknion for just over 2 years now. Before there, I held professorial positions at Southern Methodist University. Baylor College of Medicine was doing research down there, and then University of North Texas. Really, my wheelhouses are, but before coming to Teknion, but now. Do a whole bunch in Alteryx, Data Robot, Tableau, and so I'm really kind of starting to expand my offerings there, and really just. But before that was writing a lot of code in R. I developed a Y-hat package with one of my colleagues who I had as a student while I was at North Texas. And then so we developed that together. And then I spent a lot of time in multi-level modeling and co-authored the Handbook of Advanced Multi-Level Analysis with Joop Hawks. This is going to come into play a little bit at the end when we talk about, okay, what are some extensions of regression and what can we do with that? So what I'd like to start with, though, is thinking about why we need statistical testing, because often, especially if you're in business, you start looking at, some of the analytics that are coming in. And let's say you have just, your mean reporting and you're looking at it and you're going, well, we went up or we went down. Really what statistical testing is doing is it's answering the question, hey, is that observed change really due to an actual change, or is it due to the fact that maybe there's some anomalies in our data, or maybe there's a lot of error in our data? And so I just want to show you this with just a really quick example of why this is important. Okay, so let's suppose we have let's say 12 females and 8 males that are coming in. We have their cholesterol score. And we want to ask ourselves the question, is the cholesterol between our 20 patients, is there a difference between the males and females on this on our cholesterol scale? So we might look at this and go, okay, the means of all the females is 211.67, the means of males is 192.5. Okay, we look at that and go, all right, so whatever our cholesterol scale is, we look at that and we go, okay, those are different. In fact, they're almost 20 points different from each other. And we might look at that and go, hey, that's good. Yep, we're definitely seeing differences between males and females. Okay, so, but here's the problem. When I actually plot these things out, and so let's say we represent them graphically with this box and whisker plot here, is that if we look at the females, we see there's a much more of a spread of their scores on this box and whisker plot as opposed to the males. It seems the males are much more condensed and then the females are much more spread out. Now bearing in mind too that we're trying to make some huge inference based on the differences between cholesterol scores for males and females, and we only have 12 females and we only have 8 males. And sure enough, when we actually run this in a for those of you that know something about statistical testing and for wanting to test the differences between two groups, we would actually run this into what's called an independent samples t-test or a Welch two-sample t-test. And if we run this analysis, we would see, okay, right here, p-value 0.066. So this would mean we would fail to reject the null, which means that even though we observed a 20-point difference between the females to an 11.66 versus males, 192.5, this part right here, even though we observed a 20-point difference, statistically, what we're saying is that's not an actual difference. And it could be due to a number of reasons. It could be due to the fact that we only had 8 males and 12 females. It could be due to the fact that, you know, as we were looking at before, the spread of the females is not similar to the spread of the males, okay? And so what these statistical tests are trying to do is to give us some idea of really, did we get enough data, and is the data robust enough to answer the question? And in this question, in this case, the question is, are the females and males cholesterol scores different from each other? And so what the statistical test is telling us, no, it's not. They're not different from each other. Or at least, a better way to think about it is, we didn't find enough evidence to say they were different. Okay. And in hypothesis testing, which is what we do in a lot of statistical testing, all we're doing is we're stating something to be true, and we're saying, all right, did we find enough evidence to support our hypothesis, which in this case, our hypothesis is that there's no difference between the two groups, or did we find enough, or did we not find enough evidence to be able to support the hypothesis? And that's why people will say, like, I rejected the null, or I failed to reject the null, meaning I didn't find enough evidence to say they're different. So in this case, we're failing to reject this idea that, yeah, the means aren't different from each other. So there's just not enough evidence in our data. Okay, when you think about, now that's a lot of statistical ease, but when you think about your own data and what you're doing with your business, when you are actually running a business and running data through, what you are going to be doing is asking those same types of questions. And then the answer is going to be, did I have enough data to be able to say, yes, I'm going to either reject that or fail to reject that, or did I find enough evidence in my data to be able to support that? Now, this is really important, and it's kind of a nuance, but it's really important because when we start with our data analysis lifecycle, we always start with this, the business problem. And I feel that a lot of times when we're doing consulting with different companies, generally they will start with either the data or they start with the analysis. And we always strongly encourage them, okay, take a step back. We don't want to start with the data. We don't want to start with the analysis. We don't, and I always get worried when somebody when somebody meets with us and they say, hey, we need to do principal components, or we need to do, we need a regression model here. We always have to start with a question. And so that generally is one of the longer stages that statisticians like myself, we don't enjoy this part. I mean, really, we want to get, dirty with the data and, get our hands in there and get them dirty and try to, start running models and trying to test them. But really, that's kind of a naive way of moving forward, because we can run models that answer questions that nobody cared to ask. And so starting with that question is really, really important. So we get the subject matter experts, we define the unit of analysis. For example, if you're wanting to know, hey, what are daily trends like in my business, but you only capture your data every week or maybe even every month, then again, we're not going to be able to answer that question. And so defining those unit of analysis. Now, what this leads to is a really interesting quote that I read out of it, and I'm going to show you the book in just a little bit. But this quote said, your data is only as good as the questions you ask. But I would push that a little further to say, look, your answers are also, they're only as good as your data. So it's this kind of revolving and reciprocating model where we're saying, all right, your data is not any good unless you asked a good question. But when you ask that good question, you can only answer it if your data is good. So it's this cycle that goes back and forth. And this thought came from this guy named Doug Laney, and he wrote a book called Infonomics, which is just a great book. Strongly encourage that you read it, because one of the things that he really posits in there is this quote, and then I'll break this down a little bit. He says, why hasn't our organization been treating information as an asset all along? And how the heck can we hope to thrive, let alone survive, in an increasingly digital world without doing so? This has led us so far that even here at Teknion, our founder and CEO, he has, Steve Agee, what he has said is, we probably need to be encouraging people to put data on their books. Meaning that data is actually, you're constantly viewing this as an asset. And so asking those good questions, yes, really, really important. But then obtaining the data in a robust way to be able to answer those questions, you need to start thinking about your data as an asset. So when you start thinking that way, that now informs the rest of what you're going to do with your business, and actually using that data in order to move forward, in order to be able to answer the types of questions that you would want to when you're moving into predictive analytics. Okay, all right, that's a really long sermon on a really small soapbox, but I just wanted to put that out there first. All right, so if we're looking at our data analysis lifecycle, and so let's assume that we, as before, we went ahead and we defined our project really well, and we actually, we got a really good questions. And then the next stage of this is we're going to start exploring our data. Now, notice that we haven't picked our model yet, because the first thing we need to do is find out what type of data we have, how does it sit. We're going to look at exploratory analysis. We're going to do a whole bunch of effort around things like how much missingness is in our data. Are there things in our data that we don't actually, that we need to have, but we don't have? So do we need to enrich the data with like pulling in Experian data or something, or Dun & Bradstreet data in order to answer our questions better? How do we get it all into a single table so we can actually run it in a predictive manner? We will start doing feature engineering. So I'll get onto this in a little bit later, but so let's suppose that our data is, let's say gender and ethnicity come in, but we want to know in marketing, does gender matter, does ethnicity matter, but does somehow the combination of those two things matter? Well, now we're going to have to feature engineer and create a new variable that's a byproduct of those two variables. And so that we would call these in stats interaction effects. And so we want to do that. We also want to remove target leakage. So again, this is really important with time series data, that when we have information that we know in the future that can influence our current current predictions. So for example, if we were trying to predict let's say stock prices or a specific stock price, but we know all of the prices of similar stocks on that same day. Well, when we're trying to predict forward, you're also predicting you're using as a variable to predict how other stocks are going to actually behave on that future time too. That's called target leakage. And so we would actually pull those things out of our data set in order to make sure that we don't have that in there. Okay, so again, we still haven't gotten to selecting a model yet, but we've picked a really good question. We're exploring our data to see, hey, do we have the data that would actually answer this question, or what data could we use to actually answer this question? Do we need to enrich it? Do we need to add more to it? And so this feature engineering, here's a good example of why this is important. So if we look at, this is just hypothetical data that I made. So let's suppose we're looking at how much we get in sales acquisitions based on how much we're spending on advertisements. Okay, so if we look at, so that we have advertisement spend, all the way up to our markets there are $50,000 and $100,000, and we have basically our return on investment or sales acquisitions up on our y-axis. Okay, and we can see that you know, we have quite a bit of spread when we're at $50,000, but as we get out to $100,000, the return on investment is not near as good. But what we didn't think about putting in this data set, and actually didn't, if we just left this, which would actually give us some information, but it would give us false information about the relationship between ad spend and sales acquisition, because what we didn't notice is that we actually had two different sources of signal coming in. So those pink circles and the regression line that's fit on those are actually sales acquisitions from paper advertising that we did. And then electronic advertising are those blue dots. And so what you see is that we're actually seeing quite a bit more return on investment from the electronic advertising than we are from the paper advertising. And also too, it's a little bit hard to tell, but the return on investment is also steeper when we're spending more money with the electronic advertising as opposed to the paper. And so that paper costs us a lot, and the more we spend, we're not getting necessarily more return. But we are getting a little bit more return on that blue one, okay? So when we talk about feature engineering, this is the thing that we're talking about doing before we even get in to our data set of saying, all right, we may have signal coming from these two different sources, or we may need to combine some sources in order to get more information out of our data, okay? Again, all of this is done before we start building the model. All right, so finally we made it though. We've defined our objectives, we've explored our data really well, and now it's time to pick a model, okay? So in doing this, we're gonna begin that modeling. We'll select our variables based on our data exploration. We'll build competing models, meaning that we don't generally just pick one, but we pick, you know, multiple to kind of compete against each other. And then we validate those models. And so we spend time making sure those models are good going forward. So now how do you get a model is going to be the topic of kind of the rest, but I wanted to show you the rest of the life cycle. We're actually going to stop here at this third one, but I wanted to show you kind of what the intent is, and then also future webinars are going to talk about this fourth and fifth strand. So the fourth is where we kind of start interpreting and refine. So we make continued refinements. We start interpreting all of the results from those models, begin to put it into production, and then finally we do production and maintenance. So we deploy the model, and then we set up routine maintenance, whether it's a daily, it's you know, by us, or weekly by us, you know, meaning the one that built the model. Or we get a third-party tool such as Data Robot to actually run the production and maintenance of the model, you know, and then send us alerts for when we're outside of some threshold. Okay. All right. So back to this begin modeling. Right? How do we pick a model? Well, it really depends on what your dependent variable looks like. Now, I was joking with another colleague at Teknion that I spent the better part of a day one day looking at all of these. There are a lot of, you know, if you Google online, hey, how to pick a model for predictive analytics or how to select a model, that there are a lot of flowcharts. But the struggle is that the flowcharts generally start with, okay, here's the type of, you know, here's a flowchart for regression. Here's a flowchart for classification. Here's one for, you know, just logistic, or, you know, if you have binary outcomes. But it didn't really start with this question. And for me, this is the most important. Once you've decided what you are going, the type of analytics, the type of question you're going to ask, and the variable that you're going to use, meaning that outcome variable that you're going to use, that should always be the first question. So for example, if you're in a hospital and you're wanting to look at mortality rates, then you would only consider your outcome variable is going to be whether or not someone lived. Okay, it's going to be dichotomous. Let's suppose you're a bank and you're wanting to monitor, or let's say even a hedge fund manager, and you're wanting to monitor stock prices. Okay, that's continuous, or intervally, or ratio scaled. Or let's suppose you're wanting to predict whether or not, if you're in retail, okay, whether or not someone will come into your store, and then also if they come into your store, whether or not they will actually buy something. So in that, we would say that is a classification. You know, we have 3 different classifications, meaning 1 is did not enter the store, number 2 is entered and walked around, and number 3 is entered, walked around, and then actually purchased something. So we may even think of that as ordinal. But so we start with that question: what does your dependent variable look like before we're picking our model? Because the different models that we run, we're going to be a little bit confined on which models we can run based on how our dependent variable looks. Now, here's the caution. If we do this wrong, some stat packages will actually allow us to run an analysis, even though we picked the wrong type of model for the type of data variable that we have, our outcome or dependent variable that we have, for our outcome variable. Your stat package will still give you a result. Like sometimes it's not smart enough to know, hey, this is ordinal data, meaning like it's order like first place, second place, third place, and it will treat it like it's interval because it doesn't know better, right? I mean, you would have to select something that actually makes that makes sense. So this is important because we want to start selecting our model based on what our dependent variable looks like. So we can have a couple of options with this. So we can really think of our dependent variable as being 3 ways. And okay, yeah, there's actually a 4th way, but it's really hard to do. So I'll mention it, but I'm not gonna talk about it. Okay. So the first is nominal. So when we're thinking of nominal data, this is like gender. So there's no equal appearing intervals. There's one is not better than the other. Same thing with ethnicity. Yeah, so we typically think of this as categorical data, like jersey numbers. That would be a good one too, because we don't really think of, whether or not somebody has a certain number of jersey, that 12 is not better than a 13. Okay, so we might do ethnicity. We can also, might do ethnicity. And so based on if our outcome variable looks like this, it's some sort of category, okay? We have a certain group of models that we can run against that. Now, if our data is dichotomous, this really kind of is categorical data, meaning did you live or did you die? But there are certain ways that we can actually run dichotomous data. And so we may have, even though it could be categorical, it could be ordinal. So it could be, it could be a yes or no answer. It could be mortality rate, whether or not someone, mortality, or whether or not they were readmitted to a hospital. Okay. So whether or not, or just whether or not they have a specific trait. So like dichotomous could be, we're trying to predict whether or not someone has blonde hair, or whether or not they have blue eyes, or whether or not they sunburn easily. And so that's, or whether or not a cancer is present based on a whole bunch of signal coming in from a whole bunch of other variables, okay? Whether or not they have that trait, okay? And then the third way is this interval or ratio data. And this is typically data that's on a continuous scale. We call this equal appearing intervals. And by that, we mean that, yes, 2 is more than 1 and 7 is more than 6. And the distance between 1 and 2 is the same thing as the distance between 7 and 6. Okay, it's the exact same distance. So it's on equal appearing intervals, and it's on a continuous scale. Something like heartbeats per minute, right? That would be a good continuous scale. Now here's the struggle: is that sometimes we have data that's on a continuous scale that we move to a nominal scale or even to an ordinal scale. This is really, 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 really bad practice. Like we almost never want to do this. And so, however, we do it all the time. And so let me give you a good example of this. So I have a daughter that's getting ready to go to college. And so as she is getting ready, one of the things we talked about is I asked her, hey, do you know the school that you're going to? Are they on their scale? Is it just if you get an A, meaning like between a 90 or really an 89.5 and a 100, does it count as an A, or do they do like A plus, A minus scaling for your GPA? And that's important because she wants to go on to grad school. And so that, those types of things need to know. So what we've done is we've taken a variable that's on a scale from 1 to 100. It's an equal appearing interval. and we moved it to an ordinal scale. And why is that important? Because now it's not equal appearing intervals anymore. We give them a 4.0 or we give them a 3.0 or 2.0. But the difference between, in most schools, the difference between a 1.0 and a 0.0, meaning a D or an F, is not the same as because really an F on that scale is 0 to 60. And then a D is 60, or 0 to 59, and a D is 60 to 69. And then a C is a 70 to a 79, and so on and so forth, carrying it up. So what we did is we actually, we took a lot of information away from that interval ratio, and then we put it down into this ordinal scale. And then even further, we might even put it to dichotomous. I mean, that's really bad where you're taking this long scale and you're making it to be like a 0 or 1, whether or not they had it or didn't. Okay, that's really bad practice because in all of these models, we thrive on variability, meaning variability drives the bus. That's what we're trying to predict is why are people, or why are stocks, or why are some signal that we're having come in, why is it different? And so we never want to, well, I'll say not never. I mean, I can think of 1 or 2 instances, but we almost never want to take that data that's at this interval scale and push it down to dichotomous, or even really bad is somehow make that nominal. Okay, we really don't want to do that. So now here's the way to think about this. This nominal and dichotomous, we can typically think of these as classification models. And then the interval, but also some of the dichotomous, we can think of as regression models. And I'll get into why we choose which one for which in just a little bit, okay? But really, so we have classification versus regression. These are the types of models that we're going to pick. Okay? All right, so let's talk about an example of classification. Now, you may have seen something like this before. This is a basic decision tree, and it's really what we're trying to do is we're trying to predict these categorical outcomes of how fast was a person driving. What was their average speed across their trip? And so all of these trips where we're saying we're starting out of Boston, okay? And so we're saying, all right, did they start in Boston or did they not? So the way to think about this is the blues are the yeses and the reds are the nos. And so if we start out of Boston, then we said yes. Okay, so the next question we would ask is snow on the ground? And if there is snow on the ground, then the average speed was 35. But if there wasn't snow on the ground, average speed was 40. And so if they didn't leave Boston, then the next question would be were they leaving? Were they out of Atlanta? And then if it was yes, again, the snow on the ground. And so as you can tell from this, people who are driving from Atlanta with snow on the ground are decisively not as good at driving than people from Boston because they have to go 25 as opposed to 35, right? And so then we can add other what we call branches to a tree. So we can start to add more questions in there. Like, was it a weekday? Was it rush hour? But really what we're trying to do is classify our group into the 55 mile per hour people, the 25, the 20, the 40 mile per hour people, the 35 mile per hour people. We're trying to make a classification system on this. So this is what we call a decision tree, and just an example of an output that we might see from that. In this case, we have, let's see, what is it? 1, 2, 3, 4, 5. 5 different classifications: the 55 mile per hour, the 40, the 35, and the 20, the 25 and the 20. Those are our groups that we're trying to classify into, okay? So regression, now this may look really complicated, but it's not, I assure you, okay? So in regression, our observed variable, what we're trying to do is we use observed data to formulate a model about a response variable, and we're going to call that response variable y, such that a function of one or more predictors or covariates and a residual term or noise. Now, here's why this is important. I want you to see this. So this formula, and I promise you're going to feel a lot smarter after this. All right. So this formula is just basically saying, I've got some continuous outcome variable that I'm trying to predict, and we're going to call that y sub I. That means a score for a whole bunch of individuals on this outcome variable. And so I'm trying to predict that plus as the formula of some constant, we don't need to worry about that right now, and a whole bunch of predictor variables. In this case, we just have one predictor variable. And then we have a whole bunch of other stuff over here that we're going to call noise. Now, why is this important? Because in the future, when we predict someone's score based on this model that we build, we're actually not going to use that noise. But when we're building our model, not the prediction part, but when we're building our model, the amount of noise that we can reduce, or meaning the amount that we can't explain on the dependent variable, that's really what's helping us to get better models. And so another way to think about it is the smaller that this is right here, this E term, the smaller that is, the better that this stuff on the left is doing at predicting that outcome variable. So that's what we're trying to do. We're trying to minimize this with all of these variables that we're going to put over on this side in order to predict that. Okay, so that's really a simple way to think of linear regression. It's just a whole bunch of variables in this part right here. If you can see my cursor there, a whole bunch of variables in here to try to predict this thing. And we want this to be small, right? We want the error terms to be small because we want all of this to explain so there's no real error. So a perfect model would be when we can always 100% predict someone's response. Or something's response. Of course, that's never going to happen, but we try to get it as small as possible. Okay. All right. So there's regression, just really quick regression explained. All right. So now we have the nominal categorical data, because remember that was the question that we were asking is that, what does your data look like? So let's suppose it's nominal or categorical. Okay. We call this classification analysis, meaning we're trying to determine what class you belong to. Okay, or what classification you are. All right, so here are some common solutions on this. We can do decision trees, forest models, neural networks, naive Bayes classifiers, even something called predictive discriminant analysis. I'll give a lot of warning about this last one. It's really hard to do, really difficult. And in fact, if you're using like a product like Alteryx, we don't even have the ability to do that in there. And we could do it inside of something like R or SAS, but this is predictive discriminant. It's really difficult. Okay, so those are the common solutions, and we can show a little bit about how they work. But what we're looking at is most classification algorithms, they give a probability at the end of belonging to a certain category based on a series of weights applied to the features, meaning the features are the predictor variables, right? Or another way to think about it is if we're using this, the features is everything in this spot, okay? All of that stuff in there. Okay. All right. So when we're doing this, and I'm going to show an example of this in just a second of what this looks like. Really, the goal is how do we classify each of the people in our data, and then we'll build that model and we'll say, okay, now that let's try to, after we build a model, we'll validate it. We'll see how well is our model functioning. Okay. But when we have this nominal or categorical data, especially when we have multiple categories, more than 2 categories, these are the types of models we're going to use. Decision trees, forest models are really just a whole bunch of decision trees. Again, a neural network, and then Bayes classifiers, predictive discriminant analysis. Okay. Now, what about when we have just dichotomous data? Really, so we have 2 options on this. We can do classification models, as we've talked about before, or we can do logistic regression. And it's like the regression before, but really instead of predicting a singular outcome, we're kind of predicting probabilities. It's a little bit more difficult, but here is the general guidelines. So how would you know in that case, okay, our data is dichotomous. Which one, when do we use classification models? When do we use logistic regression? Okay, when does it make sense? So here's the general guidelines. So if you have a lot of features that are also categorical, meaning predictor variables that are also categorical, in that case, it makes a lot more sense to use classification models. However, if you have most of your features are that interval scale, then you would want to use logistic regression, okay? And here's why. The dummy coding is the real reason behind this. So let me show you what dummy coding is. So let's suppose we have a variable that is in our our data set that's called school, and we have 3 different schools, school A, school B, and school C. If we include this in a classification analysis, then all we need to do is enter in that one variable, and then it will nicely parse out that classification. And so we'll just say in essence, it will only charge us, if you will, for 1 degree of freedom on this. And so it makes the classification really, really easy. However, if we do this in a logistic regression model, we actually have to dummy code this variable. So because we have three different options here, then we have three variables that we're going to have to create in that logistic model. And so where you see everyone, and so we created a variable called school A, that everyone that was in school A has a 1 and everybody else has a 0. And so you can see, and then for a variable school B, if you're in school B, you get a 1, everybody else gets a 0, and then school C is the same thing. And so so as a general rule of thumb, that's why we said before, if you have a lot of features that are categorical, meaning predictor variables that are categorical, you generally want to use classification models. And if you have a lot of features that are interval, you want to use logistic regression, okay? So there's an example. So let me show you what this looks like inside of Alteryx, and so why we would actually be doing this. And so hang on, this went to sleep real quick, so let me pull this back up. But what we're going to do is give you an example inside of Alteryx that actually runs this. And so to talk about how we would handle the same type of analysis in both logistic regression and in our as a decision tree. So here's the data that I have, and this is just kind of some fake data that I made that's got, we're going to predict whether or not someone is readmitted to a hospital, so the probability of readmit. And we've got some variables. One of them is whether or not they had an in-hospital event, meaning they had some sort of event like they went into shock or something like that, or they had to be something went wrong with their heart, or they had some sort of in-hospital event. We're giving them a knowledge test on how much they know about their disease. We look at their previous admissions. And then finally, also, we look at something called comorbidities, meaning how many of these other really, so whether or not maybe they also had diabetes, whether or not they had let's say like a history of cancer or something like that. Okay. So we could run this in a logistic regression model, and then we can also run this in a decision tree. And in Alteryx, what we would do is just union those and then run a lift chart. And the idea is that this lift chart could give us information about which model is doing the best, because this dichotomous outcome, we ran it both ways. Now, if you'll remember, if we're looking at the logistic regression, that's going to be this blue line. We're going to get more what we call area under the curve. So what we're looking for is the better model is one that's kind of this higher and makes more of a steeper curve versus the decision tree. Okay, but remember what we said before is that the outcome variables, in this case, most of my outcome variables were intervally scaled, and so the logistic regression is going to take advantage of that for this dichotomous outcome, and then the decision tree won't. And so even if we look at the gains table, we can see area under the curve for the logistic regression is 0.65 or 65%. The decision tree is not much better than 50%. Okay, so that's just a little bit of an example of when we would, when we're wanting to run these type of models, both with a dichotomous outcome, because again, what we're trying to predict is whether or not they're readmitted. And because of that, these are all on an interval scale. That makes more sense for that type of modeling. Okay, all right. Now on to interval or ratio scale data. So we typically want to do in this, not typically, almost always want to do regression analysis in this. Now, again, there are many, many flavors of regression analysis. And so, and I'm going to use a first caution on this, is the complication of something called the general linear model. There are, so if we think of all statistics really belonging to this one parent, if you will, from which all statistics are derived, then we would call that one statistic general linear model, or that one type of modeling a general linear model. And we would say that, hey, regression is just a special case of that. And then really ANOVA, meaning testing for means, is really just a special case of regression. And then a t-test is just a special case of ANOVA. And so as we keep climbing up that tree, things can get more and more complicated. And so my caution is this. Again, most of the regression analysis that we do are typically kind of some canned, like again, if we're using Alteryx, we get some canned regression type statistics available to us, but we can do much more complicated models. That doesn't mean we should. Just complication is not a moniker for how good your model is. Generally, again, because for us, parsimony is going to be king, meaning that things are easily explained, things that are, have less obfuscation inside of them are good. It's as that whole Occam's razor principle applies here. Usually the simplest solution is the right one. And then the caution here also when we're doing regression analysis is that you don't use too many features that are nominally coded. Remember that nominal coding, meaning that just as we look back to the dummy coding example, when you run these in a regression analysis, it's going to create a whole bunch of dummy coded variables, and you'll have trouble really kind of parsing out what's happening inside your data set. Okay. So the good part though is that when we're doing a regression type analysis, as long as the outcome variable remains the same, comparison across different types of models is really straightforward. Okay, it's not quite as straightforward when we're doing classification analysis. You have to do a little bit of work on that end. But in this, comparing models when we're still in that regression framework and we're using the same type of dependent variable, really straightforward. Okay, all right, so let's look at an example in Alteryx also for when we're doing just a regression analysis. And so in this case, I'm going to be looking at this data set where I'm trying to predict this current spend. That's how much money someone spent when they came into our store. And that's a product of whether or not they're a rewards member, their combined income, the number of credit cards they have, and their age. So I'm trying to use these four things, meaning age, number of credit cards, combined income, and rewards member to predict their current spend. So I pulled in a tool, and actually I could pull in the regression tool if we wanted. I could click here on Predictive and pull that linear regression tool in if we wanted. But this is actually a tool that we made here at Teknion. We give it away for free. It's up on our website, and if you want more information about that, I could show you. But the reason I wanted to pull this in is because this is really interesting to me. One of the things I can do with this tool is do a little bit of outlier detection. And so if we're looking at this, what's called a QQ plot, we can see, boy, there's a good identification of row 109 and maybe row 141 that might have an outlier. Actually, I'm really not concerned about these, but I just wanted to show that there is a possibility there of being able to identify some outliers in your data. And then the other thing is the reason I like this is because we get not only in this case, the weights, meaning how much each one contributes to the overall model, but we also get something called the beta weights, the structure coefficients, and then these are called the commonalities, okay? And how basically we get information about how each variable contributes to the model in and of itself. And this is the one that I would care about right there, that variable, the combined income, 68 of the stuff that we're explaining really, 68% belongs to combined income all by itself. So that's a lot of information for me to be able to have there. But this is the type of model I would run when my outcome variable looks like this. It's continuous, this current spend variable. Okay. Now, you're probably thinking to yourself, hey, one of the things, Kyle, you didn't talk about was time series. And you're right, I didn't. We did a complete webinar back in the fall just on time series. And so we can do predictive analytics inside of time series. And it actually, it works out really great. We can do some, they can do some really great stuff, or you can do some really great stuff inside of time series. And actually, we just did one recently on how do you do time series inside of Data Robot. But for there's really kind of two types of time series. One is where you derive features based on just your outcome variable, and another one is where you put predictive variables in there to predict why things change across time. And your data typically come in, and so I just want to talk a little bit because really selecting your model is all about what your dependent variable looks like, your outcome variable looks like. A lot of times when you have time series, your data comes in like this. It's what we call wide, and so each column will represent, let's say, a different month. In this case, And so you'll have data that for all the January data will be in a column that kind of goes down January, and the same thing in February and March. Really, in order to run a time series analysis, it needs to be in what's called long format. And so where you actually pivot this stuff down into this, which is difficult sometimes to do when you have predictors and different predictors in January, or ones that actually remain constant across that entire time. So we actually, there's a lot of wrangling. We don't have time to go into that here, but the time series is important because those are some predictive models. But anytime you have data that is from, that is going across time, you don't want to do a classification or a regression modeling. You want to do time series. Now, the one thing I will say about this is that we for the most part, will do like an ARIMA or an ETS type modeling. But the multi-level time series is really where it's at for me. This is somewhat available in DataRobot, but for the most part, you're actually doing this inside of a package like R does it really well, SAS does it well, M+ does it well. But you want to add in, you want to model what we call random effects, and then you want to add in what are called time varying covariates, meaning that as we go across time, the predictors change, and they also change in somewhat in relation to whatever your outcome variable is. So DataRobot calls this a series, but in multi-level structures, we typically think of this as something called growth mixture. Okay, it's really hard to do. So if you haven't done this before and you're not familiar with it, this is, again, we'd love to talk with you more about this. It's very difficult. It's hard to monitor, but it is sometimes worth doing because you can get a lot more information about your data. Okay. All right. Also, if you are interested in time series, let me plug this book. I don't know John very well, but I do know Judy. She is an outstanding person. This is a really great book. It's really easy to read if you are looking at doing time series stuff. Okay. All right. So some final thoughts. So here's our order of operations when we're trying to pick a model. Remember, it's question, data, model. So we first come up with a really good question. We ask ourselves, do we have the data to be able to answer that? And then we start picking a model, okay? And we pick a model based on what our outcome variable looks like. It's not about how all of our data looks like, although we will when we're doing binary stuff. It does matter. But really, it's all about that question and whether or not we have the data to be able to answer that question. That's going to drive how we pick a model. Remember, we're going to ask the question about our data: is it nominal, is it dichotomous, or is it continuous or interval scaled? Okay, those are the ways that we want to think about that. Now, you remember I said before, there's really a fourth. The fourth is ordinal. That's a whole different special set of models that we probably don't want to get into. But again, too, that's going to be really hard modeling. So if we're to do like an ordinal logistic model, that's really, if you have ordinal, you only have one option for the type of models that you're going to run. Okay. The second is parsimony is king. One of the things that the temptation is to, when you're running these models, is to start to throw every piece of data you have at your outcome variable. This is generally a really bad idea because when you include just hundreds and hundreds of variables in your model, it may be that you find that some of those variables are well, there's some spurious correlations there, meaning they don't make sense and they're not replicable because you have hundreds of pieces of data in there, they're actually picking it up. Okay, and so again, parsimony is king. That whole Occam's razor principle. When you have a lot of solutions, usually the simplest one is the best and the most right. Okay? And then the last one is watch out for overfitting. Now, this is really a lot more for when you're getting into more of the complicated models, and that you start doing weird things with your error structures and things like that, just to try to get a better model. This happens a lot in time series, that we do what's called overfitting a model. And so again, if you don't know what this is, you probably haven't done it before. So you have to do some pretty interesting wrangling into overfitting. But I have seen this happen sometimes with some clients who are they'll run an analysis, and then they'll run an analysis based on the output of that analysis, and that's called when you're running let's say running a regression on the residuals or what's left over. That a lot of times will become some overfitting, and it's a weird animal. Okay, all right. So I did want to show you just some featured resources that we have up on our Teknion website. And so if you're able to get here, then you know kind of where that is. We have a lot of information up there. And then we have future webinars also. And then you can see some of those things here, okay? But what I want to do is I'm gonna pull up the QA part because we're almost out of time, and I'm gonna see if I can have this. So sharing the workflow with attendees. Yeah, so that's a great question. Someone asked, will you share the workflow with attendees? Absolutely. So Rachel is going to send out to you the live recording from this. And Rachel, if you want, we'll make this deck available to the attendees also. And so just a reminder, Rachel, to get that for us. And so
yep, we can do that.
Okay. All right. Well, thank you for it, and just remind me so that when we send that out, we'll have that in there. There's a question about the Alteryx built-in algorithms. So compared to some of the other popular frameworks, that's a really good question. I mean, limitations on the built-in algorithms. So yes, and I think though Alteryx would be the first. I mean, I'm pro Alteryx. I like it because I can do something incredibly complicated and then hand it off to the next person. And they don't have to know what I did in order to get some good results and actually be able to interpret their results. And so some of the baked in stuff I like and I don't like. For example, like if you're doing principal components in Alteryx, I don't like it very much at all because you can't control what we call the rotation techniques. And so most of them will do kind of what you need to do, but again, like we built that Y hat one because you couldn't do some of the things that I think is important to do, like looking at the beta weights, the structure coefficients, the commonalities, and then also doing some outlier detection. And so, but for the most part, they're pretty good. I like sklearn a lot. Some of the neural network stuff, especially if you're doing it in R, yeah, I would recommend that. So having said that, though, you can fully run R and Python inside of an Alteryx framework, and so that's no issue at all. Yeah. So as far as limitations on built-in, it's really limitation on how good are you inside of R or Python. The next one is I'm interested in the tool developed by Teknion. Will you be sharing all these workflows later? Yeah, so that is also, and in fact, if you go to the Teknion website and then you go to the screen that is on, the page that's on Alteryx, it's actually there. All of the tools that we develop inside of Alteryx we make available for free. Let me actually, hold on, I can actually pull that up real quick. Let me get to there real quick.
I can also post the link in the chat.
Okay, thank you. So I'm on the Teknion webpage right now. And so if we go to software platforms and then into Alteryx, and then I'm going to scroll down here there's our Alteryx toolkit and then the predictive macros. These are available for free. So we did one, and they also have videos, kind of how they work. The k-means one, what that does is it uses a clustering algorithm where it will help you determine how many clusters do you need to retain, because that's the most common question that's asked in k-means. And then also to the Y-hat regression tool, so you can download it there. Okay. So in order to get, it said actually, can you deploy this next one? Can you deploy a predictive model developed from Alteryx and create a REST API? So where do you deploy? Yes, so you can do that. So you need to, in Alteryx, you need to have Alteryx Gallery in order to do that. And so you have to have a server set up, and then you can you have a REST API that sits inside the gallery there. And so then where you would deploy it out of that service. So in the Alteryx standalone, no, I don't believe you can. I may be wrong about that. I don't believe you can. But if you have Alteryx server, so yeah, when you have the Alteryx server, that will actually work. Okay. All right. Well, hey, it looks like we are out of time. I have a number of other questions. I will try to actually reach out to you afterwards and send you information on those, the answers to those. But I just wanted to say, hey, we really appreciate y'all joining us. Look for other training sessions. And so one of the ones I think is going to be a lot of fun to do is, okay, now you've selected a model, and how do you monitor whether or not it's any good across time? So I think that will be a fun one to do later on. So Rachel, I'm going to turn it back over to you.
Thanks, Kyle. The recording for today's session will be emailed out to you guys within the next day or two. And I'll also include the workflow and any other resources that were mentioned today. But like Kyle said, be sure to check out the upcoming webinars, and thanks so much for tuning in today.